Welcome to my Advanced Physics Online. This is the last episode on vectors. If you want to watch the introduction to vectors, check the previous videos. Kindly subscribe, click on the notification bell, like, and share. This is a summary of all the operations that we can do with vectors. This will help us to predict many physical events because many quantities in physics are vector quantities. We've already established that in 2D, every singular vector is denoted by this arrow. And if that vector is say A, this vector can be written as the magnitude in the x direction and the magnitude in the y direction, like so. So this is a vector AX, x roof, then AY, y roof. There's always an angle the vector makes with the horizontal, the 2D plane. So vector A could be written as AX, x roof, plus AY, y roof. Now AX, which is the magnitude of the vector in the x direction, is equal to the magnitude of A cosine of theta, then AY, the magnitude of A sine of theta. So in totality, the overall vector A can be written as A cosine of theta x roof plus sine of theta y roof. We can expand the bracket and compare with this, and they are the same. Now this very thing is one of the operations on vectors. That vectors can be added, vectors too can be subtracted, vectors can be multiplied, and in special cases vectors can be divided. Now one addition on vector operations could be you have one vector in the 2D plane, vector A, you have another vector in the 2D plane, vector B, then you have an overall vector, vector C. Now it turns out that vector A, which is AX, x roof, AY, y roof, could be added to vector B, which will be BX, x roof, BY, y roof, because we can mimic the Cartesian plane here. Vector B also makes an angle with the horizontal. It has an x component and it has a y component, like so. So vector C is going to be equal to AX, x roof, plus AY, y roof, plus BX, x roof, plus BY, y roof. That is the arithmetic sum of the two vectors. If we group like terms, then we have AX plus BX x roof plus AY plus BY y roof. So if an overall vector such as C is the sum of two individual vectors, then the x component of the overall vector C would be the addition of the x component of their respective individual vectors, whereas the y component will also be same. So then the vector will be an enlargement of the combination of A and then that of B. So if you check very well, vector C would have an x component hitting this part, which will be the sum of the a and then the b, of course the y too. Now, vectors can also be subtracted. For instance, if you have a vector a and you want to get a zero vector, it is simply by subtracting vector a from itself. That can be written as vector a plus the negative of a. That will give you 0. So if a vector is added to its negative, it gives you 0, a 0 vector. This is what we call a 0 vector. 0 vector is a point at an origin. So if there is any vector I can call the negative of a, it will be a vector the opposite direction of a with the same magnitude. So say a particular vector is a subtraction of two vectors, say a minus b. That will simply be the subtraction of the x components, that is ax minus bx. Now both in the x roof plus ay minus by, both in the y roof direction. Now let's recall that x roof is a unit vector in the x direction, which is sometimes denoted as I. And the y roof is also sometimes denoted as j. We define a unit vector, say in the x direction, as a vector in the x direction divided by its magnitude. So given any arbitrary vector, say vector a, now its unit vector would be a roof, would be the vector a itself divided by its magnitude. And this is what we term as unit vector. This has already been explained in the previous video. Now, it is time to delve into the multiplication of vectors. There are two ways we can multiply vectors, both of which appear in physics, and we establish the mathematics. We have the dot product, the cross product. It is time to multiply vectors. One of the most common way to multiply vectors is called the dot product, which is also called the scalar product. And this appears in physics a lot in work done. Work done being the product of a force and its perpendicular distance that it moves an object through. Now, you ask yourself, how come people sat down to define the dot product? It doesn't come by somebody sitting down to create these things. Now, you chance on it, you say physics, and you establish the mathematics. Now, the dot product is established this way, that in 2D, if you have a vector A and another vector B, then A dot B is equal to, now you first take the x component of the A, the magnitude of it, which is ax, then you multiply that by the x component of the B, which is bx, then you have ax bx plus, then you take the y component of A, which is AY. You multiply by the y component of B, which is BY. You have AY times BY. That is what we call the dot product. You multiply the x component, then you add it to the multiplication of the y component. Now, an example could be you have a vector A in the xy plane with the component, say, in the x direction is 2, of course, x roof, and then 3, say, y roof. Then you have another vector B with a component, say, 5, x roof, and then say 10, y roof. So vector A is equal to 2x roof plus 3y roof. And vector B is equal to 5x roof plus 10y roof. Then you are to find A dot B. That is by multiplying the x component, 2 times 5, and then adding it to the multiplication of the y component, that is 3 times 10. And that is equal to 10, and then plus 30. Then you have 40. 40 what? Unit. Now, if it is work done, there need to be 40 joules. Physics stumbles upon lots of mathematical problems. Then we establish a mathematical concept for that. One of them is a dot product. Now, then again, if you have vector A, and then you have vector B, the dot product can be written in a different way using the angles that the respective vectors make with the horizontal. So vector A makes an angle theta A with the horizontal, and vector B makes an angle, say, theta B with the horizontal. So then it turns out that vector A, which can be written as A cos theta x roof plus A sin theta y roof, can be multiplied with, or can be dotted with, vector B, which is B cos theta x roof plus B sin theta y roof. So in effect, this is AX, this is AY, BX, BY. So the dot product A dot B would be equal to, and remember it is AX times BX. So we have A cos theta B cos theta plus A sin theta B sin theta. We have AB appearing in both sides of the quantities. So we have AB factorized out. We have cos theta. There is an omission I've made here. So this is cos theta A, cos theta A, cos theta B, cos theta B, cos theta A, cos theta B, sin theta A, sin theta B. This is A, then cos theta B, plus sin theta A, sin theta B. Now there is a trigonometric identity that if you have cos theta A, cos theta B plus sin theta A, sin theta B, it is actually written as cos bracket theta A minus theta B. So cos theta A minus theta B, if you expand this bracket, you have cos theta A, cos theta B, plus sin theta A, sin theta B. It is beyond the scope of this class for me to explain that elementary trigonometric identity. Now, cos theta A minus theta B. Theta A minus theta B is the angle between the two vectors. So the dot product will be AB, the cosine of the angle between them, which is theta. So now you see the dot product can be expressed in terms of the multiplication of the component, or the multiplication of the magnitudes of the two vectors, cosine the angle between them. Now from this we can establish so many things. So A dot B is equal to the magnitude of A, magnitude of B, the cosine of the angle between them. Now, the dot product is 0 when the angle between them is pi on 2 radians. That is 90 degrees. Because the cos of 90, or pi over 2, will be 0. The dot product will simply be the magnitudes of the two vectors multiplied when the angle between them is 0. So for two parallel vectors, if two vectors are parallel, the dot product between them will simply be the multiplication of the two magnitudes, because then the cos 0 will be 1. So two perpendicular vectors, for instance, these two vectors with an angle pi on 2 between them will have a dot product of 0. But two parallel vectors lying on top of each other, will have a dot product being the multiplication of the two magnitudes. So then you scale them. That's all on dot product for now. Now time for cross product. The next multiplication of vectors is called the cross product. And this one appears in torques and angular momentum. Now, the net torque on an object demands that we multiply two vectors in a unique way that we call the vector product or the cross product. In the two-dimensional plane, as usual, you have a vector A, you have another vector B. Now, the cross product is written as A cross B. So now, no more a dot, it's a cross. It's a vector C. But this C is a vector which is perpendicular to both vectors. So if this is A, this is B. A cross B is a vector C that is perpendicular to both vectors. And there is a way to define the cross product. In other words, given a two-dimensional plane such as this, there are two perpendiculars to vector A and B. One is coming out of the board, and imagine one going into the board. So you ask yourself, if the cross product between the two vectors is a vector C that is perpendicular to both of them, is it the one coming out or the one going in? So we are going to use a convention called the right-hand rule. Right-hand rule. The right-hand rule, or the right-hand corkscrew rule, is that A cross B. Now imagine holding this vector here as a screw, then cross B means turn it towards vector B in this direction. So then A cross B is like so. It's turning a screw like so. Because A points this way, B points this way. A cross B means you holding A and turning the screw towards B. So it is going to be in the clockwise direction. If you are screwing in the clockwise direction, what happens to the screw? The screw goes into the blackboard. If you have a screwdriver and there's a screw, then you turn it clockwise, the screw goes into the board. That is a convention. So that means that A cross B will be equal to the negative B cross A. For dot product, A dot B is equal to B dot A. But for cross product, A cross B is equal to negative B cross A. What is B cross A over here? It means holding B and turning towards A. So then the screw will go the anti-clockwise direction. And if you screw this way, the screw comes out. A cross B, the screw went in, and then B cross A, the screw comes out. So they are negative of each other. So three-dimensional space has given us an advantage that we can multiply two vectors and get a third vector which is perpendicular to both vectors which are multiplied. We call that a cross product. Before we define it better, let's go to three dimension. Now, on a two-dimensional plane, this is how a three-dimensional figure will look like. So over here, where do I put my x-axis, my y-axis, and the third axis called the z-axis? Now, it has been defined in such a way that x cross y will give you the z-axis in the positive direction, that is to the top. So already this one is named the z direction. And we are going to make sure we are putting x and y such a way that x cross y will give us a vector in the z direction. Let's try. Let's put x here, the y here. Then x cross y is turning the screw in this direction. You turn it this way. If you turn the screw like so, it will come downwards. So that means it will not give us a z direction, but it will give us a negative z. So then we reshuffle, put x here, and then put y here. Now x cross y will be a screw being turned this way, anti-clockwise. That will give us a vector in the z direction. This is a two-dimensional space. We have x-axis, y-axis, and then the z-axis. The unit vectors in these axes are x roof, y roof, and then z roof. And already it has been established that x cross y will give you z. Every vector x cross vector y will give you vector z. So clear, x cross y will give you z. So that means x roof cross y roof will give you z roof. A unit vector in the x direction cross with a unit vector in the y direction will give you a unit vector in the z direction. That is the first thing. So then it turns out that y roof cross x roof will give you negative z roof. Let's number them 1, 2, 3. And let's establish more. So now we've done x cross y, y cross x. What of x cross z? So x cross z, we turn the screw in this direction. Clockwise, it will go into the negative y direction. So 4. X cross z give us negative y. 5. Z cross x, that is holding z, turning a screw in this direction, will come in the positive direction, positive y direction. So z cross x will give you the positive y roof. Now y cross z, so hold y, cross it with z, and it's a vector screw turning anti-clockwise. to give you the positive x direction. Y cross z will give you the positive x roof. And last of all, z cross y will give you negative x roof. Now, these are what we are going to use to define the cross product better. So A cross B, let's expand A. So A cross B will be equal to, what is A? In 3 dimensions, we have AX, X roof, plus AY, Y roof, plus AZ, Z roof, cross BX, X roof, plus BY, Y roof, plus BZ, Z roof. So then we are going to expand the bracket. If you pick AX, X roof, then you multiply through the bracket here. The first quantity will give us AX times BX, X roof cross X roof. If you have X roof cross X roof, they are both pointed in the same direction. You cannot cross two vectors which are parallel. And very soon we will understand better when we define cross products using the angles between the two vectors. So this quantity will give us 0 because X roof cross X roof will give us 0. Next one, AX, X roof cross BY, Y roof. That will give us AX times BY, X roof cross Y roof. What is X roof cross Y roof? It will be 0. So we have AX, BY, Z roof. That is this and that. Next will be AX, X roof cross BZ, Z roof. That will be AX, BZ, X roof cross Z roof. Where is X roof cross Z roof? Will give us negative Y roof. So this will be minus AX, BZ, Y roof. The minus comes from here because X roof cross Z roof will give us negative Y roof. We are done with the AX. Now AY. So we have AY times BX, Y roof cross X roof. Y roof cross X roof will be negative Z roof. So this will give us minus AY, BX, Z roof with a minus. And AY, BY, Y roof cross Y roof, that will give us 0. AY, BZ, Y roof, Z roof. Y roof cross Z roof will give us X roof. That will be a plus. AY, BZ, and X roof. Last of all, we pick AZ, Z roof. Now AZ, BX, Z roof cross X roof will give us positive Y roof. So plus AZ times BX positive kind of, so AZ BX, Z roof X roof, Y roof, positive Y roof. Then AZ Z roof BY Y roof will give us Z roof cross Y roof, Z roof cross Y roof, negative X roof. So we have AZ BY X roof. And finally, this and that will give us 0 because Z roof cross Z roof will be 0. So then it turns out that A roof, vector A cross B, will give us these quantities. But let's summarize them by grouping like terms. So if we group like terms, then we are grouping the X roofs at one side, Y roofs, then Z roofs. Let's start with the X roofs. For the X roofs, we have one here, then one also here. The first one being AY BZ X roof, the minus AZ BY, of course, X roof. Then we come to Y roof. Y roof, we have AZBX AXBZ, so plus AZBX minus AXBZ Y roof. Then the Z roof, we have this and then that, so plus AX BY minus AY BX in the Z roof direction. And you can always remember this quantity, A cross B. Now, first of all, for the X roof, if you need the quantity of the vector in the X roof direction, talk about the Z and the Y. For the Z and the Y, you take AY, multiply by BZ, subtract it from AZ, and then BY. Then you get the magnitude in the X roof direction. What I mean is, you are talking about a vector with a magnitude in the X roof direction. Then you speak of magnitudes in the Y and Z, or you are talking about X. For that matter, first take A, its magnitude in the Y direction, multiply by B, its magnitude in the Z direction, then minus A, its magnitude in the Z direction, times Y, B, its magnitude in the Y direction. Then we talk about Y roof. For the Y roof, then we will talk about X and Z. So take A, AZ, multiply by BX minus AX, multiply by BZ. And then Z roof, you speak of X and Y. Take AX, multiply by BY minus AY, then times BX. And a way to remember the cross product is by using matrices. Now write the vectors down like so. Then write the unit vectors on top of them. Find the determinants of this matrix and you are cool to go. Now first off, let's find the one in the X roof direction. But for every vector, if you want to find the determinant, there's a convention. Now, positive, negative, positive. For the X roof, you cross this and that, and you are left with these four. Multiply the leading diagonal, subtract the minor diagonal. So you have AYBZ minus AZBY in the X roof direction. That's what we crossed. We are done. We clean that one. Plus, we are going to Y roof. So this is a Y roof. We cross that one. Then we cross horizontal, vertical, horizontal. Then we are left with 1, 2, 3, 4. Multiply the leading diagonal, subtract the minor diagonal. I wrote plus, but the convention is it should be negative. That's why I put negative here. This one was positive, but this should be negative, so we bring negative here. Then we multiply the leading diagonal, which happens to be AXBZ minus AZBX. Of course, this in the Y roof direction. The next multiplication is of course in the z roof. We cross that one out like so. And let me first clean this one. So like so. So we are left with the vectors ax, ay, bx, by. And this is a positive convention, so plus, multiply the leading diagonal, subtract the minor diagonal. You have ax by minus ay bx in the z roof direction. If we compare the two of these, this and that are the same. This and that are also the same. If you check through, this is a plus, but this is a negative. That's why this one has been switched here. If we push the negative through, we push the negative inside, we are going to have plus here. This will be a negative, but this will be a positive. So we switch. So then we have az bx minus ax bz. So then if we use matrices as a way to remember the cross product, the only part that will seem to be different but not different will be the middle part. See here, this is positive, but you have az bx minus ax bz. But if you use the matrices, this will be negative, but then this will be switched to be ax bz minus az bx, and if you push the negative through, they will be the same. Of course, they are always the same. That is a cross product. Now, given two vectors and the angle between them, the cross product can also be defined as a cross b is equal to the magnitude of a times the magnitude of b, the sine of the angle between them. The direction will be a cross b using the right hand rule. That's where the direction will point, but this is the magnitude. This happens to be the direction as shown in the previous part of the video, where you hold a, cross it with b, and where that screw would move to will be the direction of the product. Now this cross product appears in torque, angular momentum, some other parameters or quantities. Now the reason why we pick sine theta is that, for instance, in torque, let me highlight torque. If you have a position vector from an origin, the position vector is say r, and there's an object located at that position, you apply a force in any arbitrary direction, a force say F. Now the torque, which is written as tau, is equal to R cross F. And we define R cross F the same way we have defined this cross product here. By using the angle between them, the acute angle those two vectors make, if we are to continue R, the angle between them will be this. That will be the acute angle between them. Now, an object is located here. If you want to turn the object, see, it is a rigid body, like a circle, and you want to turn this object. Now, you realize that a quantity in the parallel direction will not turn it, but rather move it translationally. So you need a component of the force that will really turn it. That will be a perpendicular component of the force. And for that matter, you resolve the force. You have the force resolved in this way is F cos theta, which will not turn the object, but will rather move it translationally. Then you need a component in this direction, which is F sine theta, which is perpendicular to the position vector. That will rather turn it. So it is this quantity that will turn it. F sine theta will turn the object, but F cos theta do work in the translational direction, the radial direction, but we need a perpendicular to the position vector. So then it is going to be the r times f times sine theta. That will be the magnitude of that turning force. Which direction? The direction will be a vector perpendicular to both of them, in such a way that you apply the right hand screw rule, hold R, cross it with F, and turn the screw. It will come out of the blackboard, the whiteboard now. So vector A cross B is equal to AB and then sine of theta. And we can deduce so many things from it. If the angle between them is 90 degrees, and the cross product will be the product of the magnitude, because sine 90 is 1. But if the angles, or if the vectors are parallel, where the angle between them is 0, then the cross product will be 0. So two parallel vectors will have a cross product to be 0. That is why, remember, x roof cross x roof was 0. Y roof cross y roof is 0. Z roof cross z roof is 0. We would expand our understanding on cross product when it is time to talk about torques and angular momentum. Stay tuned.